Hey guys, Ms. Gosling here. In this video, you're going to be learning about simple harmonic motion, and this is our second HL extension. In this extension, we're going to focus on energy, and by the end of the video, you'll be able to graph the energy for an object in simple harmonic motion. So let's go ahead and get started. And I want to start by talking about potential energy in simple harmonic motion. And I think that you guys can probably guess what that looks like. So if I start at this position here, my potential energy is at its maximum. In the middle, my potential energy is 0. And at my position to the far right, my potential energy is at its maximum as well. So if I graph my potential energy with respect to time, starting at this point here, at my equilibrium point, I am going to see my potential energy increase as we go to our highest point. I'll see it decrease as I return to equilibrium. Then I will see it increase again as I go back up to my maximum point. My graph is going to kind of continue looking like this forever. So again, this is these points here in blue are my equilibrium points. That's when I'm at my middle. And then this first point here is going to be the far left up here. And my second point here is going to be the far right. You'll notice that my potential energy is the same in both of these positions because potential energy is, of course, a scalar. And so where I actually am with respect to 0 doesn't matter. What matters is how far I am away from it. Kinetic energy is very similar, but almost the exact opposite as well. So we know that kinetic energy is equal to 1/2 mv squared. And I know that my object is moving the fastest at this bottom point. And that is just by definition in simple harmonic motion. So my maximum kinetic energy is going to be at my highest point. Or sorry, not my highest point, my equilibrium point. I'm going to decrease in my kinetic energy as I go up to my maximum point. And when I get to that maximum point, my kinetic energy will be 0. Then that kinetic energy will increase as I return to my equilibrium, and then decrease again until I reach 0 at my high point on the right side. And then again, as I return back to equilibrium, I'm going to end up with my maximum kinetic energy, giving me a graph like so. I'm going to start with my maximum, decrease to 0, increase up to my maximum, and continue like so until my pendulum is stopped by an outside force. So what I'd like for us to think about now is the total energy in simple harmonic motion. So I have my potential energy that starts at a minimum, increases to a maximum, decreases to a minimum, and continues like so. And I have my kinetic energy that does the exact opposite. So what this means, and let me go ahead, I'll label my lines as potential energy and kinetic energy. So what this means is that my total energy is going to be constant. And this is exactly what we expect, right? Because the law of conservation of energy says that that energy cannot be created or destroyed within a closed system, we are going to treat our pendulum as a closed system, ignoring the existence of air resistance. So let's go ahead and talk takeaways. So first of all, potential energy is at a maximum when the object is changing directions, so when it's at its highest point on either side. Kinetic energy is at a maximum halfway between those points, at, of course, our equilibrium. And total energy is always going to be constant. So these are our 3 takeaways. Again, potential energy is at a maximum at our high points. Kinetic energy is at a maximum at our equilibrium point. And our total energy is constant, as it always is in a closed system. So now it's your turn to explore a little more of the detail in simple harmonic motion as you solve your problems. Best of luck, y'all, and happy solving.